Okay, so in this last lecture on the hand waving about the glass transition, I will first go back to this idea of the collective behavior in glass formation, something that I mentioned quite a number of times, and then the problem of what about characteristic length scales? Okay, and the first thing that I will mention is something that I briefly alluded to before, is this idea of the spatially heterogeneous character of the dynamics. So remember, we are always here in the supercooled liquid. Okay, so I mentioned that in when there was a question about the stretch exponential and the fact that this could be interpreted as a distribution of relaxation time. Then people thought about having different regions with different relaxation times, and then there was another set of measurements that I will not discuss in detail, which is the something I said all relaxation times basically have the same temperature dependence. Well, all but say one, which is when you measure, instead of all what I said before, the reorientations, dielectric, whatever, when you measure diffusion, translational diffusion on long distances, so something that you can measure, for instance, by light scattering, but with small optical wave vectors. So this is a long distances. What you have basically is that you have diffusion motion, and you have a diffusion constant that you can measure. And the diffusion constant, usually it goes like, by the Stokes-Einstein relation, it goes something like temperature over viscosity, something like this. So you can say, okay, temperature changes by 30%, so no big deal. This changes by 15, 16 orders of magnitude, so one over d should just follow the same behavior. Where it turns out that it was measured and then in several molecular liquids and polymers, and you can see that, in fact, this is not true. In below some temperature, below some onset or whatever, you see a deviation between the temperature dependence of those two quantities, and a deviation which is significant, not just a factor of 2 or 3, a deviation which is significant. It can be 2 or 3 orders of magnitude at Tg. So there is a kind of decoupling, between translational diffusion and rotations and viscosity. It is still a slow process, but it's just a little bit faster by a couple of orders of magnitude and viscosity, and then say the alpha relaxation time, And this again was interpreted in saying, but maybe it's because we have regions of different mobilities, and when you do translational diffusion over long distances, well, you sample basically fast regions, where when you do local reorientations of your molecule, you just sample the typical slow regions. So there was again this idea that maybe there is a distribution of regions in your system. Well, and then actually when you do computer simulations, now you can visualize your system, not only have indirect probes, or you can do also visualization by imaging of colloids, colloidal systems, suspensions on their way to the glass transition. And you see that indeed you have regions that are fast moving and slow moving, and on a given time scale. Okay, because of course, you know it cannot be on an infinite time scale because the system is homogeneous at short times. It's homogeneous at very long times when the system has relaxed. So on intermediate times, it is heterogeneous in the sense that you have fast regions and slow regions in your system, and actually the size of those regions changes when you change the temperature. Okay, so this is an observation, but of course, to make this more quantitative in terms of, for instance, a length scale associated with those dynamical heterogeneities. Let me put the word because this is something that, okay. You need some correlation functions. Some correlation function. Now, again, the usual correlation function that we already discussed cannot tell you any information on that, because what you need is an information on how the dynamics, you know, if you're slow here, how far is it correlated between being slow there, okay? So you need something that tells you at a given point, is my molecule slow or fast? So here I need at least 2 times to decide if my molecule is slow or fast. But then I want a correlation, a spatial correlation on that. So I have a distance r, and then I want to see here if in the same time the molecule is slow or fast. To see the correlation, whether are those molecules both slow, and you know this is at a distance r, or are they fast, or are they uncorrelated? Okay, so what you need is something that has 2 time here, 2 time here, and a distance here. So you need a priori a 4-point correlation function, which is of course not what you usually measure. So to put this in just simple equations, and you'll have more in Ludovic's course. He will show you how you can measure it, for instance, in computer simulations. So what you have is you have an observable. Well, I'm taking my notes so I don't mess too much. Something which will tells you, for say molecule J or atom J, what's going on between T prime and T prime plus T. Okay, so say I'm just looking at displacement, so I'm going to take the real part of, you know, my favorite function, which is Rj at T prime plus T minus Rj at T prime. When Q, again, is of the order of 2 pi over the intermolecular distance. Okay, so it's one observable. You could take another one that measures orientations instead of displacements. And then, let's say, to define a correlation function, you can, you know, define some sort of mobility field, something like this, which is simply f at a point r in space between T prime and T prime plus T. And this will just be 1 over the density of particles for convenient reasons. Sum from J equals 1 to n of this quantity times the fact that this guy is in point r at time T prime. Because it's just some local measure at point r of something which is, again, a 2-point quantity. It's a composite field, if you wish. Now, what you can do is that you can look at the average of this guy. So that will be the average dynamics okay, in the average dynamics, you will just look, in fact, at you can do the volume average and the thermal average. But of course, okay, and when you plug the definition in here, you see that this is just 1 over n sum over j, of course, of fj t prime plus t. But we know that everything is homogeneous on average. Everything is time translational invariant. So this is the same as, say, f1 for particle 1 between 0 and t. Okay, so indeed, this is the usual correlation function that I already introduced before. This is, in that case, the correlation function for this variable. So this is called the intermediate scattering function. Okay, that's not important for what we need here. And we could do it also for orientations of molecules. And we know in that thing, because it's only depends on one molecule or just one point, then it doesn't carry any information about correlations within the dynamics. So if you want to do something better, you need, as I said, a 4-point correlation function, meaning that you want to look at fluctuations, okay, in the dynamics, and how the fluctuations are correlated in space. Okay, it's the only way to get the proper information. So let's say that delta f, as usual, is f minus its average. Okay, so what you will do is just introduce a 4-point correlation function. Okay, which is traditionally called G4 of R and T. And this guy is just rho times 1 over V ddr prime of delta F R prime T prime plus T, delta F R prime plus R T prime plus T. Okay, so you see that this is exactly what I wanted. That is, now I have indeed I'm measuring correlations between delta F at point R between 2 times T prime and T prime plus T, and delta F at points R prime plus R between T prime and T prime plus T. So this is exactly giving me the information I was looking for of correlations between fluctuations in the dynamics. All right, so this function can be measured, say, in simulations, maybe in colloids by imaging. Very hard to measure, of course, in experiments on molecular liquids. Now, this is a correlation function as a function of R. So, of course, you can always define from this a correlation length, by different fitting formulas. It's the decay of the function over space, okay, as a function of R, because this function will go to 0 as R goes to infinity. And there's no infinite correlation except at critical points for that function. A correlation psi4, but that depends on T. Okay, so this is why this is usually called a dynamical correlation length. Okay, so what it means is that it's in space, but the correlation depends on the time scale at which you're looking, you're studying your correlations. Okay, so this is the dynamical correlation length that, again, has been measured in simulations. What is easier to measure would be a susceptibility. So you integrate this function over space. Okay, and this is just the integral now ddr G4 of RT. Okay, and this guy is just actually the fluctuations of the dynamics. So this is something like, again, let me make sure that I don't make any stupid mistake. So this is just n times 1 over n, 1 to n, delta fj of t prime plus t squared. So you see, this is why I'm saying that this is the average dynamics, looking just at the average of this composite function that was defined up here. And now I'm looking at the variance, okay, the second cumulant of the guy. Yes?
So the first phi of t, where you define phi of t, that decays as well.
But it decays as a function of time.
Of time, yeah.
There's no space here.
Right, so
okay.
it just decays,
yeah.
Let's say, as the particle diffuses.
Well, it decays. It's just what we said. It's the function that looks like this as a function of log t. It's the function that I looked at this morning. Okay, so that grows as you lower the temperature and has this kind of behavior. But so it is very interesting in terms of time scale, but it has no length scale. To go to length scale, you need now, again, 4 points, and this is the quantity that carries information. Now, this guy has been, let's say, measured simulations in colloids, and basically the behavior is like this. Is that it goes through a maximum, because as I said, the system is homogeneous at short times, homogeneous at long times, and the maximum is around the alpha relaxation time. Not exactly factor of 2, 4, but about the alpha relaxation time. So this function, as a function of time, has this behavior at a given temperature. It increases and goes down. Now, when you lower the temperature, what happens is that function now increases more. Tau alpha, of course, is displaced, as we know, by the 15 orders of magnitude, and you observe this kind of behavior. Okay, so t decreases, tau alpha shifts, and the maximum of the function increases. So basically, of course, if you do some, let's say, naive scaling, dimensional scaling analysis, you would say, okay, well, it goes like a volume, so this is roughly, the correlation length to the power d. Well, it's too naive. It's not exactly true. The exponent is not very clear. But let's say it scales at least like some power of the correlation length. So what this is telling us is that there is some sort of number of molecules that are correlated that increases as you decrease the temperature. And of course, because it's dependent on times, what you would do is rather look at the maximum. So you will define the psi4 where, T max close to T alpha. This is one definition which is telling you that you're choosing one point at which the correlations in the dynamics are maximum. Leo, you want to?
Yeah, just to clarify, are you stating what observed numerics or experimental phenomenology is, or are you reporting on the behavior of some model?
No, this is what is observed.
What is observed?
Yeah. I'm doing phenomenology. I'm not doing models here.
Okay. Well, okay, you could be both. You could say.
Oh, you mean being off?
No, okay. I just want to know which.
No, you're right. So this is all. This is phenomenology. Okay, so this is measured again in colloids and in simulations. Hard to access in molecular liquids. So molecular liquids, there are other ways to, let's say, approximate or estimate this function, by nonlinear dielectric relaxation or by using tricky bounds, and the behavior is the same. All right, so we know for a fact that there is an increase of correlations and of correlation length in the dynamics as you decrease the temperature. Now, the estimates, yeah.
How about the width of the peak? Does it also tell us something?
Well, let's say it tells you something. I would say spontaneously I would say no, much less interesting. Except if you want, of course, then to compare two experiments, two theories, and then, okay, you have theories that predict the whole shape, and with power laws here and there and details. And so you might be interested by having the details of the shape of the function. Okay, so my answer is at a crude first order level, we are mostly interested by the peak and the fact that it grows. If you want to compare with models and with theoretical predictions, then the shape of the function itself might be interesting. Okay?
Because I would imagine if the peak is very wide, then it's probably a little bit difficult to precisely define where you are.
Yes, exactly. But you're right. And the shape of the peak changes a little bit as you lower the temperature. Yes. But let's be at the cruder level than that. Okay? Now, all estimates of this length, there are other ways to estimate it, and Mark Ediger will probably, in a week or so, tell you about experimental measurements of all that and gives you estimates because he worked quite a bit on this phenomenon. Say, like, okay, at high temperature, there are no heterogeneous dynamics. Okay, everything is fairly homogeneous. When you lower the temperature, basically at TG, the estimates are that the length scale, let's call it Xi4, is less of the order of 5 to 10 molecular diameters. And 10 is very optimistic. Okay? So this is to give an order of magnitude of the kind of length scale that we encounter in the glass formation. In simulations, you can measure it over a shorter time range, and it increases by a factor of 5 to 6 or something like this. Okay, so this is one thing to remember, and one property of supercooled liquids. So it's a property of supercooled liquids, meaning that any theory of supercooled liquids should reproduce this thing. On the other hand, it's not very clear what is the connection between the dynamical heterogeneities and this length scale to the way the time scale itself changes with temperature. Okay, so it's not necessarily the same phenomena. And for instance, even in strong glass formers, which have Arrhenius temperature dependence, you would nonetheless expect to have a heterogeneous dynamics. Okay, something which is more intrinsic to probably slow dynamics, a lot of slow dynamics, rather than just something that directly correlates with the super Arrhenius, for instance, temperature dependence of the alpha relaxation time. Okay, so this is something which is maybe a little subtle, and again, it's not proven except in some maybe I'll say word, but maybe in some mean field limits, that there is necessarily no direct connection between those growing correlations and the super Arrhenius dependence of the relaxation time, of the slowing down. This is just to keep in mind, okay? I'm not proving anything, I'm just telling you this. Now, of course, since we'd be interested to discuss the collective behavior which is behind the slowing down, and not only that goes with the slowing down, but maybe is behind it, that means that we should also be looking for maybe other types of length scales, maybe static length scales that relate then to the growth of the barriers that I said this morning. This activated scaling had some growing length. What is it true? What could be that growing length? How one can try to describe this point. Remember, there's nothing in the usual structural correlations, the pair structure. Okay, we saw this morning. The structure factor varies a little bit, and just the usual correlation length of the density fluctuations, varies by just a few percent. So that cannot be a good candidate. And for that reason, actually, there were a lot of, and maybe there still are a lot of theories, proposals trying to do away with any sort of growing static length scale. Okay, the dynamics is spectacular. It's hard to find a growing length scale, so let's get rid of it. Maybe describe the heterogeneous dynamics, but forget the static length. Now, there is again a heuristic argument that at least asymptotically that cannot be true. Okay, and let's see what's the heuristic argument. So let's assume that you have a length, the maximum static length scale, relevant static length scale, in the system, correlation, of course, is psi. Okay, so it's some finite length scale. Now, if this is the maximum relevant one, that means that I can then basically the system is uncorrelated beyond this, and I can do the usual argument, of saying that my system is made of subsystems, each being of the size of, the length scale itself, or twice the length scale, or 3 times the length scale, so it doesn't matter, something like this. Okay? And basically, those subsystems now are almost independent from all the others. So basically, when you have a correlation length like this, and it's the maximum one, then a system of size of the order of psi will be essentially independent of all the other subsystems. So if this guy is independent from all the other subsystems, that means that the relaxation of the system now, instead of being something that has everybody here taking part in it, it can just be that you relax one system at a time, and then you relax independently another system, and then another system, and then another system. So in that case, the relaxation time of the system is just essentially the relaxation time of a subsystem. Because again, everything goes in series, like in random walk, not in parallel, so the time scale is given by this guy. Now we ask the question, okay, but then what is the relaxation time of a finite size system of length psi and of volume then psi to the d? Let's say we are at low temperature, we are, some kind of Arrhenius or activated, maybe Arrhenius is not the right term, let's say activated dynamics, again, which we know is the slowest anyhow, okay? And then we are asking ourselves, well, what is, the biggest possible barrier to relaxation that we can have in a finite system? And the biggest possible barrier, okay, delta E, scales like the volume. It's impossible to be worse than having all the degrees of freedom of your subsystem conspiring to make the barrier. Okay, so this is actually the worst case scenario. So in general, the barrier to relaxation will be less than that. And we've seen many examples of this. This morning I did nucleation. Well, when you have nucleation, you know that you have a finite size inside even that guy. You can have a smaller droplet that doesn't scale like the size of the system, but scales with a different length. Or Giulio showed also this morning, and I had showed it, you could have an interface, and of course the interface, instead of scaling like psi to the d, would scale like psi to d minus 1. Okay? So this is, again, it's not saying that the relaxation of any subsystem of size psi would have a barrier that goes like the volume. It's saying that the barrier is at most like the volume. Okay? Well, if this is the case, then that's telling you that the relaxation time of your system has to be less than some, elementary time times exponential, let's put a constant, times psi to the d over the temperature. Okay, so what we've done here, by very crude hand-waving arguments that can be, criticized and everything, no doubt, but is that your relaxation time at the temperature T is upper bounded by a formula which is again exponential. It's a activated scaling formula that we encounter again, but with the volume of the subsystem. Okay, so that's telling you that, all right, if I have a correlation length like this, you see, if now I'm saying that my relaxation time, for instance, diverges. So if it diverges, like we mentioned and Giulio repeated, it diverges, for instance, at the dynamical transition or at the mode coupling transition, well, we can say from this bound, wait a minute. If we are in a real system in 3 dimensions, or in d dimensions, but d finite, that cannot be true that it diverges without any diverging correlation length. Because, of course, if this guy goes to infinity, well, this guy at a finite temperature, well, this guy has also to go to infinity. Okay, so that's telling you one first consequence is that you cannot have in a finite dimensional system a relaxation time that diverges without, at finite temperature, at a finite non-zero temperature, without a correlation length that diverges. Okay, and this is, something which is fairly interesting as a general result. And this is hand waving, but of course this was done in a much more rigorous way by Guilhem Semerjian and Montanari in 2006, of course with more restrictive assumptions to derive the result. But let's say even with these restrictive assumptions, this is deriving the same result here of the upper bound. Okay, so well, I will come to this point. Yes, I will come to this point. Now, what it also tells us is that if the relaxation time, what I said, this is not good what I'm saying now. I want to keep this for now. If the relaxation time, as we saw, has a form of, say, tau 0 times a growing activation energy. So this is super Arrhenius. Okay, and then this is bounded by some t prime 0 exponential c psi to the d over t. Well, this is also telling you that even if there's no true divergence at a finite temperature, well, if this guy keeps growing, well, at some point, this guy also should be growing. So at some point, just because of the bound, you know that the length scale itself, psi, should be growing as t decreases. Now, it's a weak result because it's not telling you when it will start growing, because you have prefactors, because stuff do not really diverge, but it will tell you that it needs to be growing. For instance, remember one of the formula had no singularity at finite non-zero temperature. It was the Basler formula where the relaxation time goes like tau 0 exponential some constant a over t squared. Okay, well this has no finite temperature singularity, but again it tells you that nonetheless in that case psi of t should diverge as t goes to 0. Okay, so it's telling you something, that indeed what I said before, again with kind of hand-waving arguments, that if you have super Arrhenius behavior, this is indicative of collective behavior, just degrees of freedom until up to a length, of course, have to be together, conspire, have collective behavior to produce the barrier that grows and become larger than just the microscopic barriers or the bare energies. Well, this is basically telling you this in a more rigorous way. And again, even if you're super Arrhenius, even if the divergence is only at 0 temperature, then you will have nonetheless a length scale like this, a static length scale, that need to diverge at 0 temperature. So again, this is telling you that those theories that try to do away with any sort of static length scale while still having super Arrhenius behavior of this type, well, maybe they're missing something. What it doesn't tell you, again, is how big is this length scale when you are in the observation range, that is, when you're above the glass transition Tg. Okay, so this is something which, this is, a matter of principle. So as a matter of principle, you should have a static length scale that grows as the relaxation time grows in a super Arrhenius way. But again, it doesn't tell you in a quantitative way that in any supercooled liquid you will see a big growing length scale. And I will come to discuss this point a little bit more. Okay. Now, let me keep discussing again this length, because one of the nice features of the proof by Guillaume and Andrea Montanari is that you also have an idea of what is this length scale. Not that there is one, but what is it? And this is a length scale that measures what are called point-to set correlations. Okay, and this is this length scale here. So we can put a point-to set index now if we wish. What this means basically is, and this is understandable from here, is that this is indeed, how much the point here in my subsystem is correlated to the systems around it. Okay, so if I want this subsystem to be fairly independent from the others, it means that the correlation length between this guy and the surrounding, that the system size has to be larger than the correlation length between this guy and the surrounding. But to measure this, I need a correlation then between a point and the surroundings. So this is quite different than what we usually encounter in working with correlation functions. In working with correlation functions, usually what we do is that we do 2-point correlation functions or even 4-point correlation functions. Here it's more than that, because it's a correlation between a point and a whole set of points, in the surrounding. And of course, when the correlation grows, the set of points changes. So that means that it's not even the same set of points that you will have, when you lower the temperature. Okay, so this is a tricky correlation function. This is a real correlation function. So for instance, you could imagine that you have some observable that you'll have at the center of the subsystem, R. Okay, and you will have the outside world that you will call B, because this is the way Guilhem and Andrea Montanari called it. And then you will measure this guy with some function of, say, all the observables in B. And of course, you might want the connected piece. So this is a true correlation function in the bulk. Okay, so this is a property of the bulk liquid. Okay, so this is a point-to-set correlation in the bulk supercooled liquid, or liquid. This is liquid, this is liquid. This is a very weird correlation function again. This is very different from what we are used to. But okay, this is the one that is needed at least to use in the bound. So this is, again, fairly rigorous. What I maybe will tell you now, well, if you have questions, don't hesitate as usual, but I guess this is, oh, yes, okay. Go ahead. I thought there would be none. I'm sorry, it was just... that's what I'm going to do. Oh, what a good question. Yes. Well, actually, it's a correlation function. Well, let me introduce the next slide, okay, if it measures all correlation functions. In principle, it's something that indeed, if you think about it, and if you do it properly with the proper observables, it's something that is able to measure anyhow any sort of correlation, of other correlation length, static correlation length in the system, provided, again, you choose your observables in a clever way. But I'll yes. Here, yeah, but again, that was a naive. Okay, so that was just dimensional analysis. Okay, so in fact, when it's measured, for instance, in simulations, or when it's predicted by some theories, like the Moog coupling theories, it's not, and the exponent is not d. I mean, it grows with the correlation length, but it's not necessarily a volume. It can be either smaller than a volume because there's something fractal in those heterogeneities, or it can be something weird in Moog coupling theory, but it's because it's mean field. So you shouldn't take the d here too seriously, which is just naive dimensional analysis, just to relate, again, the susceptibility to a length scale as it's done, just to give an example.
Just to clarify, when you're talking about bulk and connected, are they really physical? I'm saying those balls that you're making, are they something physical, or we can move them?
You can move them. This is on any point. Okay, so this is like a true correlation length. It does not depend. I mean, you can change R, and of course you have to decide what kind of surrounding you want to take a look at. And again, in a system when you have short-range interactions, basically instead of looking at everything, the rest of the world, it would be enough to look just at the boundary of the rest of the world. Okay, so, but again, you can choose this boundary, change it, and you can move the guy. So that means that it's something which is characteristic of, you're not freezing anything here. I will nonetheless show how you can do it, do this in a moment. Yes.
In this definition, is R
R is out of B. Okay, and I will let me maybe R is here. Okay, and B is how much you have to go to forget. Yeah, to forget. And I will draw this actually to see how this is actually measured, because Ludovic Berthier well, Giulio will discuss this within theories tomorrow. This correlational length. And Ludovic Berthier will show how you can measure it in computer simulations. You don't measure it in experiments, I mean in experiments on molecular liquids, but you can measure it in computer simulations, this length. Okay. Yeah, so B is some boundary, so it tells you, where you have to go to lose correlation, basically. Now, precisely a way to do this is something that will be discussed by Ludovic and Giulio, is that you might think, again, of taking a configuration, an equilibrium. You have an equilibrium configuration, and I'm using the same notation as Giulio so that you can follow, of the system. Well, what is it? Oh, this is a very good point. I'm sorry I missed that. So this is an equilibrium configuration, chosen with the Boltzmann probability, which is there, and I will use spins to make life easier. Okay, spins. So this is spins, but you can do it for density fluctuations. This is the way it's done in computer simulations. Okay, and you're saying, all right, well, let's take a cavity, because it's easier to define B. Okay, it's the simple symmetry, and then my point R or I will be here. Okay, and I have a cavity here. Okay, so far this is just abstract. I'm not doing anything to my system, but this is now my configuration is all over. My configuration C equilibrium is all over. But what I'm doing now is that now I'm freezing the configuration outside. So now it's frozen outside, and the outside again will be B if you wish. And what I'm doing is that I'm letting the system now re-equilibrate inside when the outside is frozen. Okay, so the outside is frozen in this configuration. And then I will produce new configurations, C prime, a whole lot of configurations that depends on, this configuration frozen in B. C equilibrium frozen in B. Okay, so this re-equilibrate. So in the original configuration, I had a sigma I here, and I will have a sigma prime I, that will be here for configuration C prime, but it will equilibrate. And I can take the average of this guy over all these configurations. So this is sigma prime I, conditioned on the fact that the outside is frozen in that specific configuration. And now remember what Giulio told us about overlaps, similarity, and all this and all that. So what I want to look at is what's the similarity between the initial configuration that I had, C equilibrium, and the new configuration that I'm generating. And again, the similarity is something like, for spins, it's just the initial one that I have, times here what I have by, okay. So this is the similarity between the initial configuration and the average of all the new equilibrated configurations. And of course, all these configurations, by the way, are valid equilibrium configurations of the system. So this is again an overlap or in similarity at the center. And this is something that you can do in models, mean field models, compute this guy, or that you can modulo the fact that it's not spins, but it's, for instance, small occupation numbers that you can also compute in a liquid. Okay, so the average now, of course, is an equilibrium average, so it's the average over the initial equilibrium configuration, if you wish. But this is just an equilibrium average. No, it's the overlap at I. Okay? So this is the overlap between the original spin in this equilibrium configuration and this guy here. Okay? So that looks again like now you're doing something, weird. You're freezing, so you're putting boundary conditions that Giulio will say, and others, amorphous boundary conditions, because there's no order in the problem, and you're looking at the overlap inside, and of course then you can change R, okay, because B is defined also as a function of R, and what you expect, again, is that when R is very small, well, the outside configuration will constrain very much what you can do inside, and again, the similarity will be very high, because you can't do much. When R is very large, the system is like the bulk, so you know that this guy will just go to the disconnected thing, okay, so will just be uncorrelated. And in between, well, you'll have a length scale, which is, for a given R, you'll have an R, say, crossover, where this guy, okay, will do something like this, and this will define some length scale, or let's call it for the moment R crossover. Now, why is that a 0.2 set correlation length? Well, again, it's a fairly trivial thing, as what I did in those courses, is that if you think of what is this quantity here, well, this quantity is just, I have frozen the spins of the initial configuration, the sigma I. So this quantity here is just a function of the spins in B in the initial configuration. Okay, because I take the Boltzmann average, so of course sigma I now has been traced out. So it's only now a function of what was in B in the equilibrium configuration. So by definition, it's a trivial thing, this is a function of the spins, the same sigma as here, so the same C equilibrium, but now in the outside. Okay, so when you do this, you realize that this quantity here, well, it's exactly what I was doing here. That is, this is a 0.2 set correlation, which has nothing to do with boundary conditions and anything. It's a 0.2 set correlation in the bulk of the system. You don't have to consider now that you have frozen spins and all. It's just a correlation function, an equilibrium configuration between spins at point I and a function. It's a specific function, of course, of the spins, doing this sort of setup, but a function of the spins, outside the cavity of the ball here. What are we trying to gain? Well, first, it's a practical way to compute a 0.2 set correlation length. Okay, so this is just that something that you will see again in Ludovic's course, is that this is the way you implement computation of the 0.2 set correlation length in computer simulations. And as you will see in Giulio's course tomorrow, this is also something that you can rationalize on the basis of, let's say, the mean field theory of the rugged landscape, and how you can go beyond it by defining a length scale. Okay, so this is a procedure, this cavity procedure with freezing the spins around is something that is both convenient and interesting from the point of view of the going slightly beyond mean field theory. And the only thing that I'm showing here is that this procedure that will be used okay, by both these guys, is indeed easily shown as being just a point-to set correlation function in the in the bulk of the system. It has, say this again. No. I'm sorry. The 4 point here. It's different. Okay. It's less complicated in the sense that it has no time. Okay. This one is a static computation. Okay. This is an equilibrium static computation. So there's no need to discuss times and how the particles change between two times. On the other hand, it's a much more complicated object than a 4-point correlation function, because here you see it's a point-to-set correlation functions, with the set being changing with R and being eventually very large if the length scale is itself very large. Okay, so this is a equilibrium correlation function, but again, as I said, a weird one that goes beyond the 2 point, 3 point, 4 point, 5 point, 6 point, and so on. Okay, beyond that.
So I'm just curious, how do we define? So in the case of particles, we have a particle and we consider particles within a distance r. How do we define that distance in the system?
Oh, here, for instance, you could put the spins on a lattice. Okay, so maybe the cavity on a lattice, of course, on a cubic lattice, it's not nice to put a spherical cavity, but you could put a cube or something like this. So you could put this on a lattice. Is that answering what you were asking?
I mean, so in the case where in a system that's defined and actively connected. Oh,
all right. Well, I might answer a little bit, but Giulio will tell you that. If you truly mean field infinitely connected graph, then there's no notion of distance and metrics. Okay, so length scale means that you're going beyond mean field in some sense. So you have a real space. It can still be large dimension, whatever, but you have a real space with your real metrics, and you can define length scale. So you do not do it on a fully connected graph. This is going slightly beyond. You can do this beyond mean field. This is slightly beyond mean field, or completely beyond mean field. But Giulio will do it. Just show how you can do this beyond mean field to get information. All right. So, sorry.
Quick question. Would it be possible to extract information about decoupling between translational diffusion and rotational diffusion from this correlation function?
Well, if we had a theory of the glass transition beyond mean field, yes. We hope that we would have a theory that relates all pieces of the phenomenology to all the quantities that we can measure. So far, I would say it's a little shaky, and the answer is rather no. Now, let me just have a better description, because I don't want to, steal too much of what Ludovic and Giulio will say and show curves on that. If you have a critical point, so let's say you have the Kaufman temperature, with the true ideal glass transition. Well, what you expect is that more or less everything will be controlled by the same type of length scale. So you would expect that, okay, the dynamic length scale and the static length scale go together. Okay, so in that case, if you have the static length scale, you can predict the dynamic length scale. Hard to do, okay, but you could imagine that. Now, in mean field, what happens is, as was said, you have above this, you have a dynamical transition. Okay, so maybe it's a good point to show this again, is that when I plot 1 over t log tau, okay, you remember this was the this is the actual data, okay, from again -13 to 3, and the mean field prediction, the mode coupling theory prediction, has a, when it's empirically defined, has a divergence around here. Okay, so this would be the TD, okay, mentioned by Giulio. This is where, and again, this is exponential E of t over t, and this divergence here is t minus td to the minus gamma. Okay, so this one is power law, this one is activated. But this is because this is mean field again. And this what TG, and maybe the TK is here. All right, so this is to make the connection between the mean field prediction, and the mean field doesn't predict anything in terms of dynamics between TD and TK, because the breaking of ergodicity is here. Okay, this is what is subtle about the mean field theory of glasses. What happens is that when you do, and again this will be discussed by Dave Eichmann, is that in the mean field description and in the mode coupling theory description, you can indeed compute that 4-point correlation function and that 4-point susceptibility, and that for dynamical length scale. And what happens is that in mean field, the dynamical length scale diverges here. Okay, so this would be now a length scale, and psi4 has a divergence here. Okay, so the point to set length that Giulio will show has a divergence here, and the psi4 has a divergence here. Now, in finite dimensional systems, again, where this does not exist because, maybe a crossover at all, but you have something else, then the question again of what's the connection between psi point to set, psi4, and the relaxation time is an open question. Okay? And this is something that people are still working on to decide what's the best answer. Okay, let me now do a small estimate before I conclude. And now I will need my notes. Something that I guess Eric asked, which is, all right, let's think of, so I said this length scale is at most 5 to 10 molecular diameters. Let's get a rough estimate at this one. Ludovic will tell you what are the numbers in simulations, but let's just do an estimate. So tau of t, say, has an activated dynamic scaling. Okay, let's say it does this. And again, let's look at this. Now let's forget the mean field and the length scale. Okay. And let's look at this. So we said, all right, so this is about this is TG here. And let's get rid of TD, which is, again, the mean field thing, and say, all right, but I have maybe some onset temperature at which things really become to be super Arrhenius. And as I said, this is around 30% relative change. Okay, so here I have, say, between this and this, I have like, 14 to 15 orders of magnitude. Okay, so let's put this. So I know that log 10 of tau at Tg divided by tau it onset, not well defined, but it doesn't matter, is of the order of 14 to 15, which means that C times psi of t over Tg minus psi t onset over t onset to the psi, is of the order of 34. Now, that's not a big deal. It's just going from log 10 to log e calculation. Okay. Now, as we said, t onset over Tg, let's say, is of the order of 1.5. Okay, this is a typical number. Now, the value of this guy at the onset it's of the order of, let's say, 2 to 3. Okay, because again, the change of the change here, just goes over maybe a decade or so. So here, the dynamics are pretty fast. I mean, the change of the with temperature is pretty slow, and then it's become that it's later that becomes much faster. Okay, so if we do this and we plug these numbers, again, this is a very rough order of magnitude estimates. We have that psi of Tg divided by psi of T onset, to the exponent to the power psi is of the order of 8 to 12. Okay, so what does this tell us? So remember, we really have the 16 orders of magnitude change. Okay, we have not unreasonable numbers put here, and we were using just what we believe is maybe the explanation of what we're seeing here. That is, we're using the activated scaling. Okay, well, if you put some numbers now in the exponents, again, this is a very easy and crude estimate. Well, if psi is equal to 3, because now d equals 3, of course, I'm looking at actual liquids. So if psi equal to 3, you see that the change of psi over psi onset is of the order of 2 to, I did 2.3. Okay, so this is, for instance, what you have in the bound. Okay, this is psi equal to d. So that means that if psi is equal to d, just changing the length scale by a factor of 2 explains the 16 orders of magnitude. All right. If psi is equal to 2, well, okay, it's a bit bigger. Let me give you the numbers, or you can do it by yourself. But it's around 3, so it's 2.8, 3.5. All right, it's a bit bigger. It goes to about 3. And if psi is equal to 3 halves, the reason I mentioned 3 halves, it's a magic number in the what is called the random first order transition theory of Peter Wallinis and co-workers, which is the one based on the starting from the mean field description of gases, and then you have a change by 4 to 5.2 with the numbers I have. Okay, it's not. Okay, so a change by a factor of 5. So this is, crude estimate, but again, it's telling us something that if we have, as the empirical evidence seems to be, some sort of activated dynamic scaling that is also suggested by the upper bound, then you see that you don't need a big change of the static correlation length to explain the 16 orders of magnitude change of the relaxation time. So you have length scales. So here I was saying 5 to 10 for those lengths. Here I'm saying, let's say, 2 to 5. And with that sort of change, you could explain the slowing down of the dynamics. So this is, you can take this both ways. That is, you can say, well, okay, if I measure a small length scale while I have a widely diverging correlational length, with diverging not for real, increasing correlational length, well, this is indeed the signature of activated dynamic scaling. And for instance, this is what happens in the case of the random field Ising model. On the other hand, you can also say, well, if the correlational length increases just by such a small amount, are we sure that the connection we are making between the relaxation time and the correlational length is indeed valid, and that we're just not missing another type of explanation that would be valid for explaining the slowing down? Okay, so this is something that one has to keep in mind. That is, the time scale changes wildly. The length scale, anyhow, doesn't change much, no matter what. Okay, so this is not even a question of fear or what. This is just a simple, also, estimate of what can go on. So this is, you see, an intrinsic problem, of course, of the glass transition, is that if we had like a normal critical point, well, you have a slow time scale, you have a, diverging time scale, but the length scale grows big. You can have, by a factor of 100,000, something like this. Okay, so you can say something about coarse graining, scaling, and you can check your asymptotic predictions. Here, basically, that means that whatever you want, you will never be in a region where you can check your asymptotic predictions where the length scale is supposed to be very, very, very large. Okay? And this is an intrinsic consequence of the fact that we presumably have activated dynamic scaling in the glass transition problem. Yes? Well, again, nobody knows. If you pick not TK, but you say, I use the Vogel-Fulcher description, well, then by construction, the correlation length is infinite at T0. Okay? So if you have, of course, that goes A over T minus T0, and you're using that formula, well, you say that psi of T goes to infinity when T goes to T0. So even if you have a critical point, and it's the same, I mean, in systems where we can do, real theory, I mean, in terms of predictions and all, like the random field Ising model, it's exactly what occurs. We know we have a critical point in that case, but basically, even in experiment, it's very hard to get close to it, just because the relaxation times become so huge when the correlation length is just, has increased by a factor of 5, that it's very hard to get to the critical point. So this is something that, you might gain a little bit, again, with experiments and all, but it will be always very hard to probe the asymptotic behavior. Okay, now let me go to the conclusion in the last 15 minutes or so, which was the conclusion were supposed to be much, much, much longer, because I wanted to discuss theoretical approaches of the glass transition. But of course, I have no time at all. So I will just say a few words on theoretical approaches. They will be really minimal. So the first thing is that that it is, I think, it's some sort of warning, because of course in this room we're all discussing the mean field theory and how you go from it and all that and all this, and how you can use phase transitions and all. But the rest of the world is not always in agreement with what we're doing here on the glass transition. So the first thing to recognize, and it's just nice to keep somewhere in your mind is that first there is of course a great diversity of approaches, and basically if you think about it you could say, okay, I already mentioned that, what is it, what do you want to do? Do you want to look at collective behavior, versus just local behavior? Something that I mentioned, okay? When the length scale is anyhow not spectacular, you might say, okay, but what is important might not be that piece that grows, but might not be a better description, of something which is local, and you can forget the fact that, there is a growing correlation length. If I tell you that the correlation grows by a factor of 2, you might say, well, but maybe to explain the phenomenon, I can say it's just 1, and then try to find another kind of explanation. And people do think in those terms. Then, even if you believe that there is something which is more universal, general, whatever, you could discuss, in terms of phase transitions, what we have been doing, criticality, what we've been doing, or you can think differently and think in terms of mechanism. Okay? So just think of and I already mentioned that, that you have a, singled out dominant relaxation mechanism that you want to describe. That is, you don't care about phase transitions and criticality, you just look for a mechanism. And I gave already an example of this, which was the description of the plastic motion of metals when you shear them, and it's a theory from the 30s. It's a phenomenon that is completely non-trivial and occurs in all crystals and metals and other crystals, and also in glasses, but for a different description in those crystals. And there's a unique mechanism that was found, which is again the dislocation glide. So it's the fact that you have those topological defects in the crystals and have a specific way of moving, which is glide motion. And that explains, the general feature of plasticity in crystals and in metals. Okay, so that, why not? People are trying to do that also for glass formation. And then, of course, even if you believe that there is collective behavior that might be phase transitions, now they are not necessarily where we can place them. They can be at zero temperature, they can be higher than the T onset, stuff like this. You could have a thermodynamic approach, or let's say a static approach, versus a purely dynamical approach. And again, the rationale for the purely dynamical approach would be, okay, we know there's something changing a little bit in the statics, but why would we care about a factor of 2 or 3? Let's focus on the dynamics, and let's say that, but the dynamical heterogeneities grow at least by a factor of 5 to 10, so it's slightly bigger, so maybe we should focus on a purely dynamical explanation without any reference to the underlying statics. Okay? And there are, again, terms like dynamical facilitation, kinetically constrained models, and all. So this is a whole line of approach to the glass formation. Now, we know, again, that these are this zeroth order description, okay? Because we know, again, that cannot be true because there is a non-trivial part of the thermodynamics, for instance, with the decrease of the configurational entropy and the behavior of the heat capacity that I didn't mention. But okay, and that cannot explain it. Again, we know here that despite the fact that the length scale doesn't grow much, it does grow. And a change of a length scale by a factor of 2, 3, 4, 5 is something to be taken seriously, especially if you know that there is an amplifying mechanism to describe the relaxation time. Anyhow, great diversity. Now, the next thing that I wanted to say is that the strength of the approach in terms of a rough landscape that we're discussing here, despite the fact that it was not my favorite theory, and it might still not be, but nonetheless, there is a strength, okay, of the landscape description picture, you know, and this idea that you have rarefaction of available states. Okay, so this is a picture that goes with collective behavior, phase transitions, and thermodynamic or static description. The strength of this is that you can formulate a mean field theory of the glass transition. And when I mean mean field theory, it's just not hand-waving stuff, or you say, well, you know, this is not important, and okay, let's forget this, and fluctuations here, and I'm sure this will give that, is that you can really get something which is the equivalent of, you know, the van der Waals or the Curie-Weiss or the whatever for the glass transition. And of course, this was first derived by Peter Wallenus and his co-workers, as I said, on the basis on you know, analogies, intuitions, what was going on, especially in the landscape, and then of course was proven to be you know, exact for, say, liquids, let's say the hard sphere system, fluid or liquid, when d goes to infinity. So again, something that you probably know is that you can view the mean field in two ways. Okay? The mean field can be an approximation. You use the approximation to, like van der Waals, to describe the liquid gas in 3 dimensions. And it's its approximation, and you know, it's not right. It's an approximation. It has shortcomings, obviously. But you can also have the mean field which becomes exact in some specific limit. And that specific limit is usually when, you know, all the degrees of freedom start to interact with each other, so that you can neglect fluctuations of your local order parameter. Fluctuations are strongly suppressed by the fact that everybody interacts and talks with everybody. And this is what you have, of course, in fully connected graphs. And this is what you have in infinite dimensions, where, you know, basically you have the same mechanism. Or this is something also that you have when you have long-range interactions between your variables with some specific limit. Okay, so in those cases, you can really neglect the spatial fluctuations. Everything is, and the mean field becomes exact. Well, if you don't, well, you probably know it, but you know, you can do it just for a simple Ising model. And you know, for the simple Ising model, you know how, I'm sure, you know, on a cubic lattice or whatever, you know how to derive the mean field description of this guy, you know, for the magnetization and for the free energy as a function of the magnetization. And then you do the same calculation for the Ising model, you know, on a fully connected graph. And then you can again derive exactly this time the same quantities. As you can see that in that case, the mean field description that was an approximation in 3 dimensions becomes indeed exact when you are fully connected. Okay? And it would be exact if you're in infinite dimensional space. So this is the same idea here, is that we have now an exact mean field description of the glass transition. Now, again, infinite dimension is far from 3, but this is at least something that has been done. And what we, I guess, is emphasized in this school, and I try to emphasize also, is that at this level of mean field, you have universality of behavior. Okay, that is, in the same class. Now again, it's not the critical exponents that are important here, it's more the behavior. You know, in the same class you have universality for the behavior of the landscape. And again, as I explained the other day, the reason why people use the p-spin on the REM or to describe this is not because we are trying to mimic directly the interacting particles, it's just because the properties of the hard sphere fluid in infinite dimensions are the same as, well, roughly the same as, similar as those of the p-spin model and all those models. Okay, so this is an important point. Now, the strength of having an exact mean field, of course, is that you can compute a lot of things. For instance, and I don't think that will be discussed in this school, within mean field you can discuss the relation between glass and jamming. Okay? And this is, something that you can do because you have basically the exact solution. So you could ask yourself, if I have hard spheres, I know those hard spheres have a jamming transition. I know that in infinite dimension, those hard spheres have a glass transition, so 2 glass transitions, a dynamical one, static one. Then what about the full phase diagram? Can I connect this to jamming? And, this is possible because you have an exact solution. It's hard, okay, so I'm not, and unfortunately nobody will do it, I guess, in the school, but you can relate those two things. So once you have an exact solution, there are a lot of things that you can try to do, and to do, of course, exactly. Now, again, as I said, you can use also mean field approximations, and you can use, some approximations that become exact in hard sphere. You can use them in 3 dimensions, and then you can try to describe the real liquids with the mean field. Now there is a problem, of course, because in 3 dimensions, and that's the weakness, of course, in 3D, you have fluctuations. Spatial fluctuations of the overlap, of the density, of, anything you want to look at, you have spatial fluctuations. And those fluctuations, sometimes it's pretty benign. You just renormalize a little bit your exponents, or just it changes a little bit your critical temperature, it does stuff like this. Sometimes it's much more severe. And basically what we are seeing here, or we used to see here before I erased it, is that here it's very severe because we know, for instance, that this prediction of mean field is wrong. So it's not that it's slightly displaced, somewhere else. It's just that the whole dynamical transition disappears. Maybe you can see the echo, the vestige of it, okay? But it disappears. And then, as I said, the mean field doesn't tell you beans about the dynamics in this region. So basically, the mean field misses the activated dynamic scaling because the activated dynamic scaling is due to fluctuations, thermal fluctuations. Okay? So having an exact mean field solution doesn't tell you anything, except if you go beyond it, okay? But just the mean field, about thermal activation and the role of fluctuations in general. So the question is, of course, everybody knows that. I'm not saying that I'm discovering this, okay? There's just the people doing mean field. Walliness said that from the beginning, for instance. So what you do, as usual, is that you can say, okay, well then there are 2 strategies, okay, for fluctuations. And I will conclude just with this. Okay, 2 strategies. One is, I would say, the standard one that is used. So, okay, you have your mean field, And what you do is that you include fluctuations. So what you do to include fluctuations? Well, I described it this morning. You can do nucleation and instantons. Okay, and that gives you some sort of activated scaling, as I described. And you can do renormalization group to describe, include your fluctuations, and change the whole picture. The problem is that, of course, everybody would like to do this in the case of the glass transition, but it's very hard to do. So up to now, the steps that we've been able, or people have been able to do beyond mean field in terms of, using, for instance, those classical tools are, let's say, rather limited. It's not that there is no progress. It's not that there are no phenomenological descriptions. But, it's very hard to implement the usual program of statistical mechanics, that is, mean field, nucleation, instantons, RG. This is well described, by the way, in a paper by Francesco, which is called, it's not a paper, but it's on arXiv. That was his habilitation thesis, Theory of Simple Glasses. The parallel with the usual statistical mechanical treatment of phase transitions. I have the arXiv. Well, you can find it, but it's 90. Okay, so this is the standard route, but it's not easy. Now the other one is that, okay, well, let's try to look directly at what are, basically guess the important fluctuations in 3D. Okay, directly. Forget the mean field. Okay, you say the mean field. Okay, well, again, infinite dimensions is too far from 3 dimensions. Some of the concepts here are too fragile to fluctuations. As I said, metastable states, it's a very fragile concept to fluctuations. So let's forget that and try to do something else. Okay? And it's basically what people doing, for instance, purely dynamical theories with this concept of dynamical facilitation have tried to do by looking just at fluctuations in terms of mobility fields. It's also what we tried to do in the old days by looking just at specific aspect of the structure and locally preferred structures and frustration and all, and seeing how this would generate the important fluctuations in 3 dimensions. This has not been more successful than this. Okay, so this is not like, haha, one of those is better than the others. We're at a point where those approaches are, again, very limited. They are not the full explanation, obviously, of the glass transition. And those approaches are very well defined. One knows what we want to do, but they are very hard to implement. Okay? So basically, I would say this is where we are in terms of the glass transition problem. But this is, again, maybe a personal view, and other people, maybe even in the room, might disagree with me. But this is okay. Anyhow, what would be my conclusion on this? So if you have questions, please go ahead.
So when you say it's a great time to invest energy in a really hard theory, if you're a student that came for, say,
I don't remember how you. That's what I was supposed to say. Did I miss this point? Well, okay, yes. This is. So you see, the program at least is clear. So if you are super smart students, ready to work on a really challenging problem, but with super great guys as advisors and collaborators and all. Well, this is a very nice problem, okay? Thank you for reminding me.
So will you comment on the upper critical dimension of the glass transition? Do we know anything about
Okay. Yeah, let me comment on this. The one comment is about the onset, not the onset, sorry, the dynamical, transition. The dynamical transition that was explained by Giulio is like a spinodal. Okay, so it's actually a little more complicated. It's like a spinodal in a random field. Okay, so you would expect naively that the upper critical dimension is 8. Okay, so above 8, you have certain exponents. Below 8, you have to change the exponents. But as I said, unfortunately, it's worse than that, because a spinodal is always destroyed in finite dimensions, no matter what's the dimension. So, in fact, for a spinodal, there is no upper critical dimension. So you might have a crossover, some exponents that you might define on a limited scale that might change between above 8 and below 8, but the spinodal is always destroyed by rare events. Okay, so there is no spinodal in finite dimensions. Now, TK, the Kaufman temperature, the static temperature, well, this one could survive, of course, in finite dimensions. And, you know, I don't know what's the state-of-the-art discussion about what are the, again, the critical dimensions. The upper critical dimension, as far as I know, is not considered as something known or important. Do you have any comments on that? No. So it's unknown. And the lower critical dimension, which might be more important or not, is, say, something which is, again, debated. People are working on it and all. But it's thought that, let's say, in 2 dimensions, for instance, you wouldn't have finite temperature TK anyhow. Okay, but this is, again, this is still part of the work that is in progress, and a work that needs bright students and very motivated students, because this is very exciting. Well, I think that first, the theory could reproduce the main aspects of the phenomenology. So you need to describe the super-Arrhenius behavior of the relaxation time at a theory level, okay? So not just as a fitting formula. So I think this is something that would be important, and you need to describe all the aspects that I gave today and the days before. Now, the question is, again, and I also stress that, is just because, you know, a theory, I believe, in terms of a general theory, will be something which is collective. Okay? And again, since there's a balance between, you know, the need for molecular details and the need for collective details, it means that the fit or the reproduction or the prediction of the phenomenology will need adjustable parameters. There's no doubt. You know, even a general theory, in general, will just need adjustable parameters. Okay, so that means that you need to add as many important aspects of the phenomenology as possible to constrain the theory. as I showed you, if you just say you want to reproduce the super Arrhenius behavior, well, you have zillions of pseudo theories, real theories, models, you know, that indeed reproduce it and fit all the data for all liquids. Now, if you ask on top of it to reproduce the decrease of the configurational entropy, well, it's a little harder. Of course, you need to have, you know, very little in the structure. You need to say something about the point to set, about the dynamical heterogeneities, about the plateau. As I said, it's non-trivial to the plateau in the relaxation function. And, you know, the fact that those nonlinear susceptibilities, for instance, increase as you decrease the temperature. So there are constraints, and so far, not many theories are able to describe all those aspects. And I don't see any more constraints from the experiments, that's just what I said. Then there is the internal consistency, of course, of the theory. Again, if you have a theory that goes from mean field and add in a reasonable